solids of revolution is just kind of what they suggest, and that is if you had a shape and you rotated it around an axis, then what would happen? Now, as it just so happens, I've got an amazing, absolutely amazing physical demonstration here for you. So imagine some curve that you have, and you're going to rotate a shape around an axis. So what's going to happen when you rotate that shape around an axis? Oh, ooh, ah, right. So it traces out, it sweeps out a volume, all right? And that's what we're going to find today is those volumes of a solid of revolution. Now, our approach is going to be a lot like what we did when we were working with Riemann sums. We're just going to focus on one little area. And let me remind you what we did with Riemann sums. So let's start out with just one rectangle. Well, let's see, there's a couple there. But to find the areas here in these curves, what we did was we said, all right, let's just find the area of one rectangle, and then we took the limit as you added more and more rectangles and added up those areas, and eventually that limit approaches the exact area, becomes the exact area, which was our Riemann integral. So we're going to do something similar. We're going to follow what happens to just one slice. So let's take a look at what happens with one slice. So in particular, try and envision what happens to this one slice as I rotate this around, say, the x-axis. So as I rotate it around the x-axis, can you suggest or see what kind of a shape that's going to sweep out when I rotate that around an x-axis? A disk, yeah, nice. It's going to rotate around in the form of a disk. And so what we're going to do is we're going to add up the volume of those disks. Now this is some technical work that we're going to kind of avoid, but this is the volume of one disk. It's the square of the radius times pi times the thickness. That limit is going to turn into a Riemann integral. And this is where we're going to concentrate our efforts, is setting up that integral. Now what's going to help us out is the same kind of dx and dy slices that we did when we started working with this stuff back when we were working with areas. So let's start with this one. Let's see here. So what we're going to do is start by rotating this, and notice that we're rotating this around the x-axis. So I'll do that. Rotate that around the x-axis, and we're going to take a slice. Let's take a slice through here and see what happens to that one slice. So, okay. Now what's going to happen to that one slice, as James mentioned, is that we're going to get, when that rotates around the x-axis, we're going to get a disk, or a disk. So let me just try and draw a little disk here for ourselves. Looks more like a hockey puck, and that's good because this is still hockey season, even though the Red Wings are out of the playoffs. We want to find the volume of that one disk. So let's see. See if we can't find the volume of that one disk. Now, the nice thing about this is it's kind of just an area that's been dragged up. So to find the volume, I'm just going to need the area of the circle. Do you remember the formula for the area of a circle? Pi r squared times the thickness. What's the thickness of this slice here? Dx, nice. So pi r squared times dx. That's going to be the volume of one disk. So let's see what we can put in for r. We need to figure out what the radius is. So the radius is the distance from some point on this curve to the x-axis. That's going to be r. What do you think that height is going to be? Call that point x and y. The height is really going to be the top point minus the bottom point. Now, this might seem like an annoying detail here, but I'm doing it not so much for this problem, but to set things up for later problems. The height is going to be this distance. Now that's going to have coordinates of x and 0. Height is going to be y minus 0. All right, well that's not really all that great, it's just y. But in looking at things here, notice that I've got a dx term. That dx term means that I have to have this expression in terms of x. So what can I replace y with in terms of x? X plus 1. So x plus 1 is the radius. And so putting that together with this expression, I get pi times x plus 1 squared times dx. So that's the volume of one disk. I keep on wanting to say washer, but it's a disk. We'll get to the washer stuff soon enough. Well, that's great, but I don't want just the volume of one disk. I need to add up the volume of all such disks. So what's happening if you wanted to kind of look at it from a Desmos kind of perspective or something like that is we calculated the volume of one disk, but we got to add up the volume of all such disks. So this one, this one, this one, this one, etc. And the way we do that, the way we add up all these different volumes is by integrating. So let's take a look at this area here and decide where we're going to integrate. This is going to be our integrand. So it's going to be the integrand of pi times x plus 1 squared dx. Well, what do you think should be the limits of integration? 0 to 2. Because the farthest left that I can take a slice and still be in this region is at 0. So 0, and then up here to 2, like that. So great. Now it's up to you. You can take the pi out here. Actually, you could solve this with a u substitution if you wanted to. It doesn't almost feel like it's really worth the work. There's a lot of possibilities here. You could square this out and then integrate it, etc. But the thing is, I'm probably going to want an exact answer. So let's do it this way. Let's do it with our graphing calculator just because I don't want to take the time to play around with the antiderivative of a polynomial. I think you guys are pretty good at that. In fact, another thing I think you're pretty good at is the numerical integration. Remind me, where do you have to go to get the numerical integration?
Math 9.
Math 9, like a course of Math 9s. So that's kind of good. I don't want you to get problems wrong because you make a mistake integrating a polynomial. So Math 9, 0 to 2. And then we've got to put in here x plus 1 in parentheses and then square it. Of course, your calculator is demanding like I am. It wants a dx. I have mine in the wrong mode because I was teaching college algebra yesterday, so let me change that down to function mode. So that looks good there. Let's go back and put in, well, you know, it'll work with n. It should work with n, I think. There you go. Now, what I'm going to want is a decimal value, or as a nice fraction here. So let's hit the math key. Well, that's a great question. Suppose I put in pi with my integral. So let me go back here and type in a pi, and then let's go up here and grab the integral. If I do that, and then I hit the math key, answer to fraction, it can't figure it out because it's no longer a fraction. Pi is not a rational number. So what we'll do is we'll just add the pi after we figure out the rest.
Oh, because it'll be an exact answer.
Yeah, so that way we get the nice exact answer. So 26 pi over 3 is what I'd be looking for. 26 pi over 3. Great. So there's our first one. So in general, what you're going to do is take a slice. Now that slice has to be perpendicular to the axis of rotation. I'm not sure if you noticed it or not, but there's something on your handout that's kind of like screaming out that your slice must be perpendicular to the axis of rotation. So don't overlook that part. That's going to become a big deal, especially not in this course, but in Calc 2, when we start taking slices parallel to the axis of rotation, that's going to be something called the shell method. Right now we're going to work with the disc of washer method. So you can be happy that we're not working with the shell method right now, but you will see that in Calc 2.
Is the axis of the rotation going to, like, is there a way the rotation, oh, it says about the x-axis, never mind.
Yeah, so about the x-axis there, about the x-axis here. But before we leave here, we're going to do the x-axis and the y-axis, and we're going to do around, I think the line y equals 1 or something else. So, yeah, we will get a variety of things to work with. All right, if you look here, this next one's for you. So, wow, all right, I guess that means we'll have to flip things over and go to example C for our next one. So before we leave here, I'm going to have you work on a bunch. And again, we've got one around the x-axis. So I like to kind of do one of these little arrows here to remind me that I'm rotating around the x-axis. And since I'm rotating around the x-axis, am I going to take a dx slice or a dy slice? What do you think? Dx. Has to be dx because it's perpendicular to our axis of rotation. So let's do it in salmon this time. There's my dx slice.
That's a pain.
I know. Salmon was the color of my hood when I got my master's degree. So I don't know, I just kind of go with salmon. Any case, let's find the volume of one slice here, or it's going to be one washer, because, not washer, disc. Because when this rotates around the x-axis, it's going to sweep out one disc. So volume of one disc. There we go. So we need a radius. And again, just for a matter of habit, I want to get you, good with these things. We need to figure out the radius. So the radius is going to be this distance here. R is going to be y minus 0, top minus bottom, or just y. What am I going to replace y with this time? Yeah, e to the x. So y equals e to the x. Thanks, Ethan. Volume of one disk is going to be pi r squared, in this case dx, times its thickness. Okay, and that's going to be pi times e to the x squared dx. Looking good there. What happens when I square e to the x? Do I get e to the x squared, or do I get something else? E to the 2x. Good, because these exponents multiply each other. So that's going to be pi e to the 2x dx. Okay. Let's see about finding the volume of this entire solid of revolution. Can you envision what that would look like if you rotate this around the x-axis? It's going to look like the end of a trumpet, really, kind of this, flaring out of a horn. In any case, let's find that volume. I'm going to move up a little bit because I think I'm going to need the room. So let's see. Integral, I'll take the pi out here, e to the 2x dx. What should be my limits of integration? Negative 2 to 2. Now you guys are really good about spotting something on the last exam. We have a symmetric interval, but is this an even function? No. Even function would have what kind of a look to it? Yeah, it'd be symmetric with respect to the y-axis. So we can't do anything fun like double the integral or something like that. Now, the one problem that we have is we know what the antiderivative of e to the x is, but what about e to the 2x? Yeah. kind of stuck on that one a little bit. So what can we do? If we don't know what the antiderivative is,
Use a calculator.
yeah, no, we're not going to do this one on the calculator. We're actually going to do this one exact this time. What could I do to find the antiderivative here? A U substitution, good. That's your only integration technique right now, only integration trick that we have. So, yeah, that's pretty much what we got to do. Let's see, that's going to be U of X. What should I let U equal? Just the 2x. So we'll call it U equals 2x. And let's save ourselves a step. Du is going to be 2 dx. Okay. Now, looking in our integrand, I've got a dx term, so I want to solve for dx over here. So let's do that. That's going to be 1/2 of du equals dx. And there's one more thing that I want to do and need to do so I can do my integration. What would that be?
Take U of 2 and negative 2.
Yeah, I need to change my limits, right? So let's put in U of 2 and U of negative 2. So let's see, I'll do it this way. U and U. 2 and negative 2. 2 and negative 2. So 2 times 2 and 2 times negative 2. And I'll get some new limits. 2 and negative 2. Those limits are going to be 4 and negative 4, respectively. Okay, good. Let's put those in here. Equals 4 and negative 4. All right, let's clean this up then. Integral of pi of from negative 4 to 4 of e to the u times 1/2 of du. We'll take the 1/2 out front, so it's going to give me pi over 2, integral from negative 4 to 4 of e to the u du. What's the integral of e to the u du? Rahana? Yeah, e to the u. Thank you. So it's going to be pi over 2, negative 4 to 4 of e to the u. The du disappears after we find the antiderivative. Plug in the limits, e to the 4 minus e to the negative 4, and that's a good place to leave it. That's a nice exact answer. It's not going to get any prettier than that, I don't think. I mean, you could get common denominators and such, but that's a good place to leave it, right there. Nice. If you wanted to, if you're a little bit nervous and insecure about your integration, what could you do to check it?
Plug it in.
Plug it in where?
Math 9.
Math 9, yeah. So what you would have to do if you wanted to check it is you would give it this integral, and you're going to get a numerical value for that, and compare it to the numerical value when you plug that into your calculator. So you can just make sure you didn't make a mistake along the way in working with your integral. All right. How are we looking on example C? Yes, question.
Or when we have the y minus 0,
Mhm.
if it was like y started at 1 or negative 1, would we
Yeah.
carry over that to the x value? So e to the
Yeah.
x.
That's heading our way.
Oh, okay.
Is that at some point we're not going to rotate necessarily around the x-axis or y-axis anymore. We're going to rotate around something else, and that's what I want to build you up towards. So I don't want it to be a big shock when we get there. So good question. Yeah, that won't stay 0 forever. But these are some of the early examples, so I want to give you, an ease into things a little bit. Anything else on example C here? What's different about example D?
Rotating over the y-axis.
Yeah, rotating around the y-axis. So, all right. Let's see. So what kind of a slice am I going to take this time? Yeah, I'm going to take a dy slice. So let's rotate around the y-axis, this case. And dy slice. So let's see, that's going to be dy in terms of thickness. We're still going to find the volume of one disk. So the volume is going to be pi r squared times dy. Now that dy serves a nice purpose for us here. It's reminding us that we have to set up things with respect to y. This radius needs to be a function of y as opposed to r. You shouldn't have mismatched variables in your integrand. So if you have a function of x here and a dy here, there's something wrong. All right, they need to match. So we need to figure out what the radius is going to be. Now when we're dealing with something around the x-axis, the radius was top minus bottom. In the case of rotating around a vertical axis, it's going to be the rightmost endpoint minus the leftmost endpoint. So in our case, the radius is going to be this point here, x and y, minus this point here, which would be 0 and y. So your initial expression for the radius is just going to be x minus 0, right minus left. But we know that this is a dy term. So I want to redo this in terms of y. I need to solve for x and replace that with y. So what am I going to do here? I don't have an expression for y.
Solve for what?
Solve for y. All right, good. How would we solve for y? Yeah, we'll start by squaring everything, sure. So x equals 2 square roots of 7y. If I square everything, then I get x squared equals 4 times 7y. What would y equal? Yeah. X squared over 28 equals y. Beautiful. Good on that one?
No. Because the 2 is outside of the group, I divided by 2 first.
If you divide by 2 first, then you'll end up with a 4 underneath the x squared term, and then when you divide by 7 again, to get the y by itself, that'll multiply the 4 times the 7. It'll still put a 28 there. So what you did is fine. Nothing wrong with the order in which you did those things. It's just a different choice than what we made. Bob Real, good on that? Cool, thank you. All right, so that's going to be our radius then, is going to be x squared over 28. And let's see, we need to put that in to try and find the volume of one disk. So that's going to be pi times x squared over 28 squared.
Don't we want y?
Yeah, we wanted y.
Which part are you?
Yeah, I screwed up, didn't I? Well, let's see here. You know what? I already had. Sorry. I had my expression that I should have used here, right? Yeah, I'm just so much in the habit of solving for x's. All right, so let's see here. There we go. Never happened. So yeah, we actually had the expression we needed right there. Silly me. let's put that back in and solve for, or simplify our expression for our volume. So it's going to be 2 times square root of 7y dy. See, where I caught myself as I was looking at, wait a minute, we got x's and y's. You can't have that as part of your integrand. Your integrand needs to be of one expression. So 2 square root of 7y. When I square this, Gabrielle, you were kind of mentioning something there that seems relevant. That term's going to get squared. The square root's going to get squared. I'll end up with 4, and then 7, and then y, and then dy. And finally, 28 pi dy. 28 pi y dy as the volume of one disk. Nice. All right, so we've got the volume of one disk, but we want to add up the volume of all such disks. So what's that going to look like when we add up the volume of all such disks? How are we going to do that? Yeah, we're going to integrate. 28 pi y dy. What should be the limits of my integration? So what you want to be careful of is that the limits of integration should reflect where this dy slice can move to and still be in this region. So what's the lowest that it can move down to? 0. What's the highest that it can move up to? So 0 to 3. Let's take the 28 pi out in front. And we just need the antiderivative of y. What's the antiderivative of y going to be? Y squared over 2. The 2 and the 28 are going to cancel, so it's going to leave me with 14 pi. And I'll plug in the 3 here. So it's going to be 14 pi 3 to 0 times y squared. 14 pi times 9 minus 0. And that's what, 126 pi? 126 pi. Now if we had units here, if this was in like inches or feet or miles or whatever units, what should I write for the units if I had units? If this was measured in feet, yeah, this would be in cubic units, right? Just to give you a little reminder that volume would be in cubic units, but since we're not working with any particular units, it's good enough to leave this one here. Okay. How we look on example D here? So a little bit of a twist there. We had to rotate around a different axis. Keep in mind that you always want to take that slice perpendicular to your axis for rotation. Okay, so let's move on to example E, where we're going to continue to work with these volumes of solids of revolution. We're going back to rotating around the x-axis. This time we've got a couple different functions. We've got y equals 7 minus x squared. And then this line here, y equals 3. But we're still going to rotate around the x-axis. Where's our slice going to be taken? Are we going to take a dx slice or dy slice? Dx slice. All right, so let's do our dx slice. And I sense a quietness or an ease about the class here. If you notice anything a little different about what's going to happen when we rotate this around the x-axis. Yeah, I'm going to get a hole here, right? Because this figure isn't flush with my axis of rotation. So, bummer. That's going to give me a different figure. So let me see if I can't draw something here to kind of reflect that. So we're no longer going to have a nice disc shape, what we're instead going to have is a washer. All right, so now for that washer, we're going to have to deal with two different radii. You're going to have an outer radius and an inner radius. The inner radius I'm going to call R1, the outer radius you're going to call R2. So this is now a washer. I want to find the volume of one washer. Realistically, what you can think of is finding the volume of this as if it were a disk, and then subtracting out the middle piece, right? Because that's really what you've got. You've got a hole, and that hole is, you know, basically another cylinder. So this is what it's going to shake out as. It's going to shake out as pi times the outer radius squared minus the inner radius squared times the thickness, which is dx. We're just going to need to be careful about our expressions here. Are we okay where we're getting this formula? Basically, I factored out the pi from both of these, but you've got pi r2 squared. That's going to be the outer radius, so that's going to help you find the volume of the outside disk, minus pi r1 squared. That's going to be part of our calculation of the volume of the inside disk. Okay, so let's take a look here. We need some expressions. This first one, should I label that R1 or R2? R1. And the outer one, that's going to be our R2. For R1, it's just going to be 3 minus 0, or just 3. That's going to be our radius for that one. What about R2? 7 minus x squared minus 0, or just 7 minus x squared. Nice. Nice. All right, let's plug those into this expression here then. Find the volume of one washer. So it's going to be pi times 7 minus x squared squared minus 3 squared dx. You guys want to review integrating a polynomial, or you want to spend our time on other things? It's up to you. Other things? Okay. Let's just clean this up a little bit. That's the volume of one washer. We want to find the volume of all such washers. So what could you do? Integrate. We'll take the pi out in front. Now here's a good question. What are the limits of integration? Negative 2 to 2. Now you can see that because you've got a nice graph there. And I might as well get rid of the 3 squared and just write it as 9. But what if I didn't have a nice graph, or what if it wasn't labeled? How would you find the limits of integration if it wasn't nicely labeled? Yeah, you'd have to set y equals 3 equal to 7 minus x squared. So when you solve there, you'll end up with 2 and negative 2. So that point's going to be 2 and 3. This point's going to be negative 2 and 3. So yeah, keep in mind that you might have to solve for those kinds of things. Negative 2 to 2. Now, because we're not going to do this one out by hand, doesn't matter so much. But is there anything you notice about this function or this integral? Yeah, it's a symmetric integral. So if you're stuck doing this by hand, maybe your instructor had a bad day and wanted you to do this stuff by hand, then you could just by doubling this, and it's going to be a little bit easier. Is it a lot easier? Probably not, but you know, every little bit helps. Dx. So let's again kind of bail out and do a math 9 on this thing. So math 9. And I'm just going to plug it in without the fancy symmetric trick there. 7 minus x squared squared again minus 9, and of course dx. Ooh, all right. Kind of a big one there. Wow, nice household number there for you. 1472 over 15 times what? Pi. Yeah, let's not forget the pi. So 1472 over 15 times pi. Nice.
Will you put it back up on this? Thank you. Sorry.
Yeah, no worries, no worries.
Where did we get the, oh, because we went 0 to 2. Got it.
Yep, yep.
But then when we calculated it, we went back to -2 to 2.
Yeah, you know, it doesn't matter. The calculator doesn't really care if you have a 0 here or not. It doesn't really make it easier for the calculator. It does for us because we end up substituting in our limits, but yeah, for the calculator, it's not a big deal. All right, looking good, looking good. Let's see, I think I got 1 or 2 more that I want to do here. Any other comments or thoughts on this one? So the big difference for us here was that we didn't get a disc, we got a washer. And one thing that I want you to be clear on and understand is that unless this figure is completely flush with your axis for rotation, you are going to get a washer. So expect that.
Why is it called a washer and not a disc?
Because it's got a hole in it. It's got a hole in it.
You know, like a bolt and water can mount.
Oh, got it. I'm thinking of like CDs as discs.
Sure, it looks
Oh,
like
yeah.
that too. Yeah.
That has a
Bigger
hole in
though.
it, yeah.
Iris?
Wouldn't the height of Ireland change after the intersection points on y equals 3?
Yeah, but that goes past the region, right?
Okay.
So we only need to worry about the height of R1 up to this point where they intersect. So, yeah, good observation. Mage?
So it's like kind of you use the washer method for like the problems that have like the area that's not grayed out basically.
Yeah, it's when there's a gap between the grayed out area and your axis of rotation. So our axis of rotation, let me make that very clear this way. This is our axis of rotation. And because this gray figure isn't completely touching the axis of rotation, that's why you have a gap. That's why you got a washer. Now over here, with example D, for instance, this was our axis of rotation. Looking back, you can see that this figure was completely flush with the axis of rotation. There's no gap. There's no space between those things. And the same thing for example C and example A. So that's why we're using a disk method here and a washer method here. So thanks for the question. Anything else? These are good questions. I appreciate it. All right. Let's take a look at example F. I'll give you a minute to kind of stare at this. And I'm going to ask you to decide 2 questions.
Says professor, but I'm not student.
I know. The professor part is that these are the examples I'm doing. A little bit later today, you're going to go back and fill in the gaps with these. So we'll do this one together. But right now, what I want you to ask yourself and answer for yourself is these 2 questions. What kind of a slice are you going to take? And are you going to get a disc or a washer? Now think about it for a few seconds and then compare notes with a neighbor. See what you think. Disk or washer? dy or dx? John, Antonio needs a neighbor. You guys in agreement on this? Lucas? You and Keegan? All right. Well, I'll call on you then. Let's see. We're going to rotate this around the y-axis. So first things first, Lucas. What kind of a slice are we going to take? dy or dx? dy. Good. Keegan, how about, are we going to use a disk or a washer?
That would be more like
A bowl. Yeah, the overall shape's going to be a bowl. But when we take this slice and we calculate the volume of what happens with this one slice, is that going to be a disk or a washer? Washer. Good, because again, you've got this gap here. And that's what creates a washer method as opposed to a disk method. So, nice. All right, let's see if we can't find the volume of one washer. Volume of one washer. And we're going to need a couple things here. So it's going to be a pi r2 squared minus r1 squared. And then, Lucas, you told us that that was going to be a dy slice. You're correct there. Perpendicular axis of rotation. So, okay, this is going to be our two radii. This one and this one. So the inner one's going to be our R1, the outer one's going to be our R2. And let's take a look at these expressions that we have here. And I'll start with the inner radius. So the inner radius, R1. Boy. Let's try it again. R1. That's better. That's going to be this point minus this point. So let's see, that's going to be coming from this function, which is our y equals 4x. So it's going to be x minus 0 for that radius. But I need to solve for x in terms of y, so I can make a replacement. What would x equal in terms of y?
1/4.
Yeah, 1/4. Thanks, James. 1/4 y. I'm going to do the same thing for this one. Call this a general point. Call it x and y. R2 is again going to be x minus 0. This time I've got a different expression here. I'm going to solve this one for x in terms of y. So what's that going to look like? If I solve for x here, what would I get? Square root of y. Good. So x equals the square root of y. And we'll use the positive square root there. So square root of y. Or you could also write y to the 1/2. Either one is fine.
Plus or minus.
No, you don't have to write the plus or minus.
It starts at 0 or because it's volume?
Because the minus one would actually be on the other side of the
Okay,
y-axis.
so it could be a negative.
And one other thing, when we square this, when you take and plug that in here and square it, if you had a negative there, it's just going to square out anyways. So we're lucky in that regard. Now, let's see. Let's plug those things in here. So it's going to be pi times 1/4 y squared minus square root of y squared dy. And that'll simplify a little bit more to pi times 1/16 y squared minus y dy. Okay, not bad. Are we comfortable with where we got our expression for the volume of one washer? Mage.
So, the two numbers that you, like in the blue that you on the top.
Yes.
Like I.
The radii.
See how you got them about, like, if you, let's say, took the provided numbers and then solved it for y, but like, can you like explain again, like, how you did it the way you did it, like, you did the x minus 0?
Yeah. The x minus 0 stuff is just building up to something we're going to do coming up shortly. And I think we're going to see it with, I think we'll see it with problem I and J, is that we're not always going to rotate around the x-axis or the y-axis. So when you're rotating around an axis, regardless of what it is, you have to calculate these radii, these distances. And so those distances, in terms of the x direction, are going to be the rightmost point minus the leftmost point. Now it's not really written, but it could be understood that the coordinates here are going to be some height of y, but on the y-axis you're going to have an x-coordinate of 0. So when you find the distance between these 2 points, it's going to be, x, y, or it's going to be x minus 0 is your distance there, and then again x minus 0 is going to be your distance here. These are different x, y points, but you're still going to get that distance, that horizontal length, and then you realize, oh, well, this is in terms of x, I got to rewrite it in terms of y because I've got a dy term right here. So you're working with it horizontally. Couple problems. Where am I?
I think that R1, R2
Yeah.
switched.
Did I switch these R1, R2? Okay, thank you. Let's see. Okay. Let's see. Is there a quick way to fix this? No.
Plus and a minus on the left.
Yeah, I can just put a minus out here, which would reverse the direction of those, and then we'd be okay. Yeah, let's just do it over here, this way. So the volume's going to end up being, and yeah, you're right, I mixed up my R1 and R2. I apologize. So pi times square root of y squared minus 1/4 y squared dy is going to be pi times y minus 1/16 y squared dy. And looking pretty good on that. Let's see if we can't figure out the volume of this shape, which I think, Keegan, you mentioned it's going to look kind of like a bowl, with kind of a cone as the center, but the outside is going to have more of a bowl shape. To do that, we need to integrate. What are our limits of integration going to be for this particular problem? Yeah, you want to keep in mind where your dy slices can be taken. Now the smallest dy slice is going to be down here at 0. The highest dy slice is going to be up here at 16. So we're going to integrate this between 0 and 16. 0 to 16. Let's take the pi out here. Y minus 1/16 y squared dy. I might actually do this one out as opposed to always bailing with fn int. And what's that going to look like? So that's going to be that's going to be pi from 0 to 16. Jameson, I need a couple antiderivatives here.
It's going to be y squared over 2, and then,
You can just leave the 1/16 out here and integrate the y cubed.
okay, yeah, y cubed over 2.
Nice. All right, so that's going to simplify to 0 to 16 of y squared over 2 minus y cubed over 48. So the big chore really is to plug in the 16. 16 squared would be 256, divided by 2 would be 128. All right, so it's going to be pi times 128. 16 cubed would be what, 4,096? I don't know, help me out there. I was never very good at math. 4,096? Whoa, whoa, give it up, hey, pretty good. All right, so 4,096 divided by 48, let's see, you're going to end up with a 3 in the denominator, 16, 4, I don't know, 512? No. What is it? 256? All right, yeah, half that, 256. 256 over 3. Now let's clean that up just a little bit more here, and I'm going to get lazy at this point, which after all that work doesn't feel like too bad a thing. But 128 minus 256 divided by 3, and then hit the answer to fraction key. Yeah, 128 over 3. So overall, pi times 128 over 3, or 128 pi over 3. Nice. Nice.
Jumping back on this one.
Yes, please.
When we determined R1 was 1/4 y, and then R2 was the
Square root.
square root of y,
Yes.
why did we do two different things? Couldn't it just be... Oh, because it's different.
Because yeah, the distance.
got it.
So your outer radius comes from the outside edge of this function, which comes from your y equals 4x squared term, and the inside radius comes from y equals 4x. So yeah, that's why we're doing different terms up here for R1 and R2. Good with that, Christian?
Yeah, it's just, I realized the other times it was just a straight line. Like a
Yeah,
solid number.
that does happen occasionally, that you have a solid line, so it's constant, as there was the case in example E. So yeah, nice. Okay, I think I got one more that I want to do, and that'd be example I. So let's move over to example I. So one of the things I want to remind you is that sometimes you're going to need to find some of these points yourself. Like for instance, the point where these two graphs cross each other. Y equals x squared, x equals y squared. How would you find those 2 points if you didn't know it and you didn't have a nice good graph? Yeah, set the equations equal to each other and solve. Now in this case it does happen to work out that it solves at 1, 1. So we've got that, 1, 1. But how about the line y equals 1? What does the line y equals 1 look like? All right, straight line diagonally like that, or horizontal? Good. So nice horizontal line here. And there's something else to note about this problem. That horizontal line is now your axis of rotation, right? Because we're rotating around the line y equals 1. Ooh. So y equals 1. That's our axis of rotation. So all along today, when we've been calculating the radius, I've done right minus left, top minus bottom. Now we're going to get something other than a couple zeros. So we're going to have to be a little bit careful about this. Let me pick a point here. Let's see, Harley, is this going to be a dx slice or a dy slice? Got to vote for dx. Laura, is she right?
Yeah.
All right, good. Dx slice, nice. And Ethan, is this going to be a disc or washer method? All All right, got to vote for a washer. Holly, do you agree? Washer? Yeah, it's look like a washer. Can anyone articulate why? Why this is a washer and not a disc? Yes.
Like a void in space.
Yeah, this figure isn't flush with your axis of rotation. So, all right. Now, let's put a couple points on this, and I'm going to be a little bit more careful about it here than I have been with some of the other ones. I'll give that one coordinates of x and y. And in a complete lack of inspiration, I'll give this other one coordinates of x and y. Now, I see, I need two different things here. I need this distance here and this one here. This is going to be my R2. That's going to be my outer radius because it's the farthest away from the axis of rotation. This is going to be my R1. So let's draw ourselves a nice little function here. A nice little washer, I should say. Okay, and let's squeeze in an inner radius. So I need an R1, which is going to be here, and then this distance is going to be R2. All right, we're going to be a little bit more careful with our R1 and R2. Now the point on this line here, even if we're doing these general coordinates, the point on this line here, we can specify a little bit more than we could with our previous ones. I know, well, I don't know what the x-coordinate is. The x-coordinate is just going to be x, but I do know what the y-coordinate is. That's going to be 1. So it's no longer just a 0 like it has been for a couple other problems. So if you'd like, try and write down for yourself R1 and R2. Start out by just doing top minus bottom. Don't worry about x or y coordinates right now. We are going to be subtracting the y coordinates. Don't worry about it writing in x coordinates just yet. Just write it in terms of y coordinates. What expression am I going to write for R1?
1 minus y.
Yeah, 1 minus y. And 1 minus y again, although it's a different y. And now I've got to go back and figure out, all right, well, what is y going to be for this inner radius? And that's where I need to understand these graphs a little bit more. So the first one I've got is y equals x squared. The second one I got is x equals y squared. Which graph do you think is which? Well, what does y equals x squared generally look like?
Parabola.
A parabola. And it's going to open up, right? So it kind of feels like it should be that. And then this one, well, we don't typically deal with parabolas that face sideways in this course, but we can. That's exactly what this is going to be. It's going to be a parabola that faces sideways. You could solve for that and graph it if you solve for y. It'd be square root of x equals y. The negative root would be the part that lies below the x-axis. So we'll just deal with the positive root. So this one right here is y equals the square root of x. And this one over here is y equals x squared. Okay, so let's fill some things in here. That's going to be 1 minus y, and y is going to get replaced with the square root of x, right? Square root of x. And then this one over here is going to be 1 minus square, no, not square root of x, how about x squared? X squared, that. Yeah, x squared is going to be your outside radius. Square root of x is going to be your inside radius. Yes?
Is R1 generally always like a top function?
It depends on the axis of rotation. So in this case, if I move this y equals 1 down to y equals -3, then the roles of R1 and R2 are going to reverse because the outer radius and the inner radius are going to change if I have something down here for an axis of rotation. So it kind of depends on the position of your radius, or of your axis of rotation. Let's fill in the expression here. Pi times R2 squared minus R1 squared. And that's going to be a dx thickness. That dx is there to remind you that these expressions should be in terms of x. You shouldn't have x and y in the same integrand. So R2, see I'm nervous now. All right, 1 minus x squared, squared again, and 1 minus square root of x squared, and then dx. Now the integral gets really, really messy here, but let's do at least this much. Let's come up with the integrand. I'll leave the pi out in front. 1 minus x squared squared minus 1 minus square root of x squared again dx. There's one thing you need to supply. What is it? Limits of integration. What are the limits of integration? 0 to 1. Nice. Okay. Are we okay with the setup here? And one thing I can do, sometimes I'll do it on various exams, is just ask you to set it up, let you finish with fn int, or maybe just ask for the setup. But to me, the important part is that you be able to set these things up. All right, we have software and other things like that that can do all these kinds of things, but you have to be able to get the setup. So are we okay with that part there? All right, let's fast forward to the happy ending then. The happy ending is hidden right over here. It's 11 pi over 30. So 11 pi over 30. Yay. Oops. Okay. Anything else about example I here? If not, then I'm going to stop things here for the video anyways. All right. Good deal.